Hi, my name's Anika,
And my name's Harris.
and our last team member is Ohm, and our project is Projections versus Play, harnessing time series to forecast athlete performance. So the motivation behind this project stems from the desire to predict player performance in NBA games to create a competitive edge in the betting market. While real-world performance is impossible to predict precisely, we believe that there was some correlation between past performance and future performance based on player tendencies. Our hypothesis is that by analyzing a player's recent performances, example where they shoot from, how often they shoot, and the opponent defense, we can uncover patterns that enable a competitive edge in the betting market. The problem we hope to address is building a machine learning model that uses time series data to predict a player's future performance using past shooting tendencies in specific areas on the court. This model will help us understand whether time-aware models can outperform traditional projection methods. So here's what our data inputs and outputs look like. For inputs, we started with player stats, so that's real player performance and shot by court region, opponent stats, so the opponent defensive rating by zone, and then contextual information such as the home, the rest, the situational awareness in the game performance. And then our outputs are shot volume by zone, so the shots taken from each of the predefined zones. For example, left three, right three, above the break, so a quick overview of our methodology. We started by formulating our problem, and then we took our data sets and started to prepare this data so that it was useful to us as well as feature engineer. So coming up with which features are important as well as doing an analysis on this original data. We then developed our baseline model and then fine-tuned and improved this model. And lastly, we deployed all of our visualizations on a Vercel app so that it's easy to access and visualize. So more about our data source. We originally had a very large data set, and then we cleaned this and removed 11 players from the data set and over 16,000 rows. So we ended up with 14,000 entries and 430 active players. We have data for multiple games per player from the 2024 season, including points, rebounds, and assists, defensive rating by zone, a player's shot chart, rest time between games, and actual versus projections for each player. Our baseline model started with a random forest regressor. And the reason we use this is because random forests are able to handle non-linear relationships well. It also provides a really easy way to interpret, and it's very robust to overfitting with proper hyperparameters. So this is very important because player performance data is obviously very complex and non-linear. We started with points, assists, and rebounds for our features, and we used lag features to organize this with 100 estimators and a random state of 42. In order to evaluate our baseline model, we used four different scores. So the mean squared error, which measures the actual squared difference between predicted and actual values, the mean absolute error, which measures the average absolute difference between predicted and actual values, the R2 score, which indicates how well the model explains the variance in the variables, and lastly, the custom accuracy score, which was something we created, which measures what proportion of predictions fall within 10%, which is what we designated for this score. Looking at our baseline model performance, we can see that it's not the best. Predicted players were expected with points with over a 42-point error, which is a very, very high error per game. In addition, we only got a 0.44 R-squared score, and we aimed to reach almost 0.8. So this was not ideal. In addition, our mean absolute error was over 5 points, which is very high. And when looking at a game and shots, we had less than 16% for our custom accuracy.
Okay, so we obviously wanted to improve this model, and we knew that we had to do something different. That baseline model didn't include some of the newer stats or features that we wanted to look at. We realized there wasn't a high enough correlation between just the points and projected stats for a player to actually get some useful data out of it. So we changed our end goal a little bit to say what we wanted to find was rather shot attempts rather than predicting exactly the score. And with that, we found a lot of success. We incorporated defensive blocks by zone, right? So their defensive rating. We added a player shot chart, the rest time between games, and performance per game. So the model predicts shot percentage by court region and how many shots a player will take in that region. And so just a really quick demo of what we have. This is the data that we were looking at. This is how the player shoots, where they're shooting from. You can do a visualization. This was all the data that we'd collected. The real meat of what we're looking at is right here. So for every single game in a specific season, you can see between the actual shots taken in a game and what the model predicted for that specific game. And this we found to be it was fair. It did a fairly good job, and we'll go look at that now. You can see if you wanted to check our data, you can find it right here. But to go back and take a look at this, our results show that our improved model was a huge leap forward. We were within 8 points if you convert the shot zone to points. We were within 8 points, which is a huge improvement from the 42 points that we were off. And another big thing is that in our custom accuracy score, only one of the models had an 18% accuracy, but all of the other ones were in the high 60s, 70s. And so yeah, extremely performant and a huge improvement from our last model. And for our prior work, Anika and Om have prior experience working with machine learning models, specifically for classification problems, and I have past experience working with static sports models. Here are references.